Hi everyone, this is Dr. Nak and we're going to go over section 8.1, Simplify Expressions with Roots. So let's first notice the difference between square and a square root. So if n squared equals to m, then m is the square of n. And in the square root, if n squared equals to m, then n is a square root of m. So for an example, let's take a look at when n equals to maybe 5. So do you see that 5 squared equals to 25, right? Then 25 is the square of 5. And then similarly, if 5 squared is going to be 25, then 5 is the square root of 25. And the notation for the square root looks like this. Square root of 25 equals to 5. So we call this notation as square root. And if I put the little tiny 3 in between there, this is called the cube root. And if I have a 4 there, it's going to be fourth root and so forth. So only the square root doesn't have a little number on there. So either way, if you look at this symbol, this is same thing as this. Okay, now whoever sits inside of the radical is called the radicand. So if I have something like square root of m, then we say that m is the radicand. And of course, this notation here is the radical sign. Just a little vocabularies here. Let's do some examples. So example 1, simplify part A, square root of 144. So basically this is asking you square of what number gives 144. So this little question mark is going to be the answer for the square root of 144. Can you guys think of any number? How about 12 squared? So do you notice that 12 squared gives 144? Therefore, square root of 144 is going to be just 12. Now let's look at part B, negative square root of 64. Alright, so let's simplify this a little bit. So first, let's just stare at the square root of 64. So the question is, what square is going to give us 64? Well, that's 8, isn't it? 8 squared gives 64. Therefore, the square root of 64 is going to be just 8. But notice that there is a minus sign on the front of it. So what's going to happen is that our answer is going to be negative 8. Now let's look at part C. Square root of negative 64. Now notice the difference between B and a C. The huge difference is that that negative sign for this particular problem is inside of the radical. So the radicand is negative 64. Whereas for part B, just positive 64 was the radicand. Okay, so let's do the same thing. So what we need to do is ask ourselves, what squared is going to give us negative 64? Alright, do you see something weird happening? Remember, if you square a number, whether the number is positive or negative, do you see that your answer is always going to be positive? Which means that there is no real number equal to square root of negative 64. So the square root of a negative number is not going to be a real number. So the answer is going to be not a real number. And this will make more sense to you when we started to talk about complex numbers, but we'll deal with that later on. Okay, now let's go with another definition. It says that if b to the n equals to a, then b is an nth root of a. And the notation for that is what you see right there. Now we call that the nth root of a, and n is called the index of the radical. So this is called the index. And then again, a is the radicand. Now let's talk about the properties of nth root of a. So given that nth root of a, I don't know what the number a is, if n is even, then nth root of a is a real number provided that a is greater or equal to 0. And nth root of a is not going to be a real number if a is strictly less than 0. So basically it's telling you that if n is even, meaning maybe like square root, fourth root, and sixth root, your radicand must be a positive number in order for it to be defined. And if the radicand is negative, it is not going to be a real number, or we can just say it's undefined. So let me just write it. So when n is even, then nth root, pretend that's like a square root or fourth root of negative numbers, it's going to become not a real number. Or we can say undefined. But if the radicand is positive or 0, you're good to go. You're going to have a real number coming out of nth root of a. Now, when n is odd, such as cube root, fifth root, seventh root, no matter what number you're going to plug it in, it's always going to come out to be a real number. So meaning that your radicand can be positive, negative, or zeros. Let's take a look at example 2, simplify fourth root of 81. So let's do the same thing as what we did before. So you're going to have to ask yourself, what to the fourth power is going to give us 81? Okay, so if you're not too sure, break this down into a prime factor tree. Do you guys remember doing this? 81. Can you think of what times what gives 81? 9 and a 9? All right, and then what? This is 3, 3. And 3, 3. So it looks like we have 4 copies of 3's. And then this is telling us that 3 to the fourth power is going to give us 81. So here we're going to have 3 to the fourth equals to 81. Therefore, fourth root of 81 is going to be 3. Part B, let's look at fourth root of negative 81. Uh-oh, do you see what's going to happen there? What's our answer? Is this is not going to be a real number because given the eventh root, you cannot have a negative number inside of there. So in this case, this is not a real number. Let's look at part C, cube root of 216. Well, our answer is going to be some kind of a real number because you're given the cube root. You can have positive, negative, zeros as a radicand. So if you cannot think of what to the third power is going to give us 216, break it down. So I'm going to break it down as 216 in a prime tree. It doesn't matter how you break it, but since this is an even number, I know for 2 is going to go in. So 2 times what's going to give us 216? So that's same thing as 216 divided by 2. What the heck is that? 108? Alright, well 108 it's still an even number, so for sure I know that 2 is going to go in. So 2 times 54 is going to give us, what is that? 108. Now this is still even, so let's go with 2 times what? 27? And then 27 is same thing as 3 times 9, and then this is going to be 3 times 3. Okay, so this is telling us that 216 equals to 2 to the 3 copies of 2's, 2 to the third times 3 to the third. Look, so this is same thing as 2 times 3 to the third power, which is 6 to the third. So it looks like 6 to the third is going to give us a 216. So let me write it. So here we're going to have 6 to the third is going to give us 216. So therefore, our answer is going to be just 6. What the heck? Let's do another one. Fifth root of 1024. Okay, so the question is, what to the fifth power is going to give us 1024? Ugh, so I can't think of it off the bat, so I'm going to break this down again. So 1024. So that's gonna be divisible by 2 for sure because that's even. So that's gonna give us 512, is that right? And then if I divide that guy by 2, we're gonna have, what is that, 256? And then that's still even, so we can divide it by 2 again. And that's gonna be 128. Ugh. And 128 can be divided by 2 again. So here you're gonna have 2 times, what is that, 64? All right, and then 64 is 8 times 8. 2 times 4. Oh my gosh, 2 times 4, 2, 2. 2, 2. All right, we got this. So how many 2's do we got going on? 1, 2, 3, 4, 5, 6, 7, 8, 9, and a 10? Dang. All right, so 1024 is 2 to the 10th power. Okay, so let me just box this because it's all blending in together as my side work here. All right, but the thing is, I want to come up with a number such that if I take the 5th power on that, that's going to be equal to 1024. But we just discovered that 2 to the 10th is 1024. So basically what we need to do is we need to rewrite 2 to the 10th into something to the 5th power, meaning this. So do you see that we just discovered this to be 2 to the 10th power? But the thing is, I want to make this into a something to the 5th power. Alright, so now let's take a look. No matter what, base 2 better be there. Now remember this property. Let me just change the color. If you have a to the m to the n, remember you multiply them. So this is a to the, multiply the exponents. What I mean is m times n. So think about it. What times 5 is going to give us 10? Well, I think that's 2, isn't it? So if I put a 2 there, what do you think? Is that going to give us 2 to the 10th back? I believe so because of this property right here. All right. Don't worry, we're going to practice more of this in details in a little bit. But here, so what we just discovered is that 2 to the 2nd power is 4. So we got 4 to the 5th power equals to 1024. So we could finally insert 4 in here. So therefore, the 5th root of 1024 is going to be 4. Okay, now let's take a look at something a little bit different. Example 3, estimate each root between 2 consecutive whole numbers. So part A, square root of 105. So to do this, think of the perfect square numbers close to 105. Okay, so here is my chart of the number and its square root. So notice that I just jot down the perfect squares, which is 1, 4, 9, 16, 25, and so forth. Those are perfectly squared numbers. Alright, so for instance, let's just look at 9, number 9. Square root of that is 3. So we say that 9 is a perfect squared because 3 squared gives 9. Same thing as, let's look at 36. Square root of 36 is 6, and then we know that 6 squared equals to 36. So we say that 36 is a perfect square. So first what we need to do is jot down the number 105 and then where that's going to fall in between. Alright, so it looks like 105 is going to be between 100 and 121. Do you agree? Alright, now 100 is a perfect squared, and then 121 is a perfect squared because 10 squared is 100 and then 11 squared is going to give us 121. Alright, now let's just try to write this out. So we just found that 105 is between 100 and 121. And notice that, again, 100 and 121 are both perfectly squared numbers. So here, if I take the square root on everything, let me see, should I rewrite the problem? Yeah. All right, so let's take a look at that. Because look what the question's asking. Estimate each root between two consecutive whole numbers. And we want to estimate square root of 105. So that's the reason why I took the square root on everything. So that tells us that, well, square root of 105 is going to be between, well, square root of 100 is 10, and square root of 121 is going to be 11. Therefore, square root of 105 should be between 10 and 11. Now, if you put this on the calculator, let me see, square root of, let me do this, 105. Actually, this is going to give us 10.2469577. So clearly that's between 10 and 11. But I think this is what the question's asking, so I'm going to box that. But just for kicks, if you type this in the calculator, approximate value is going to be 10.2. Let's take a look at another one. Let's go with the cube root of 43. So we're going to do the same thing, but instead of square root, we're given the cube root. So here I made the chart. So let's look at it. Now, if the number is 1, cube root of 1 is 1. Cube root of 8 is 2 because 2 to the third power is going to give us 8. Now notice that 3 to the third is going to give us 27. Therefore, cube root of 27 is 3. And cube root of 64 is 4. And cube root of 5 is going to be 5 because 5 to the third give us 125. Alright, so we're going to do the same thing. So let's first jot down where the 43 is going to be. 43. So 43 better be between 27 and 64. And 27 and 64 are perfect cubed numbers. So let me do the same thing. So what I'm going to do is 27 less than 43 less than, and then 64. Now we're going to take the cube root on everything because we want to estimate where the cube root of 43 is going to lie in between. Alright, but cube root of 27 is 3. And cube root of 64 is going to be 4. So this is what the question's asking you to find. Now, if you type this in the calculator, let me just bring it over here. Let me see. This is going to give us approximately 3.5, which lies between 3 and a 4, so it makes sense. Alright, next topic is simplifying odd and even roots. So it says that for any integer n greater or equal to 2, nth root of a to the n becomes a if n is odd. And nth root of a to the n becomes the absolute value of a if n is even. This is because of this fact. Let me see, how do I explain this? Remember when you guys, when we had a cube root, fifth root, and so forth? Whoever sits inside of it can be positive, negative, or 0. Right? So that's why nth root of a to the n is just going to become a, and a can be positive, negative, or 0. Now, when n was even, such as square root and fourth root, whoever sits inside of the radical must be positive no matter what. So by putting the absolute value around that numerical value a, guarantees that whoever sits inside of the eventh root is going to become positive, so which will be defined. Now this also tells you like something like this. So suppose I got a cube root of, I don't know, 2 to the third. That's going to give us just a 2 back. So basically, if the root and the power matches up, what's going to happen is that you can think of it as they're going to cancel each other out, and it's going to just give us the 2 back. And then same thing, suppose I got to make me like a fourth root of 2 to the fourth. Since the root and the power matches up, you can think of it as they're going to cancel each other out, and what you're going to have is just a 2 back. Let's do some examples. So example 4, simplify. Fifth root of p to the fifth. Well, in this case, n is even, so what's going to happen is that you can think of it as the root and power is going to match up, so they're going to cancel each other out, and what's going to be left is just p. So that's just the answer. Now let's look at b, fourth root of y to the fourth. So in this case, remember, you don't know the value of y, so y can be positive or negative here. So in this case, what we need to do is we need to put an absolute value bar around the y. And then again, the fourth root and power of 4, you can think of it as they're going to cancel each other out. So our answer is going to be absolute value of y. So now you're probably wondering, well, how come you didn't put an absolute value bar for this particular problem that we did? Well, if I derive this very carefully, this is what's happening. So we got fourth root of 2 to the fourth. Well, since this is an eventh root, our answer is going to be just absolute value of 2. But what's absolute value of 2? Well, it's just 2. That's why I just wrote this answer as 2. Now let's take a look at example 5, something a little bit different. Simplify square root of x to the 6th. Now if we want to use this property, nth root of a to the n just becomes an absolute value of a, in this case because we're given the square root. What we need to do is this number, the index and then the power on a must match up. So the game is this. Your job is to, I shouldn't say your job, our job is to rewrite x to the 6th in terms of something to the second power because you're given the square root. Remember there was an invisible little 2 sitting there? Okay, so x to the, what to the second power is going to give us x to the 6th? Well, I think, remember you got to multiply those exponents, so how about 3? Because remember, if you have x to the m to the n, this is x to the m times n. And now, index and then the power matches up. You can think of it, they're going to cancel each other out, and what's going to come out is, remember this is an eventh root, so absolute value is necessary. So here you're going to have absolute of just x to the 3rd. So that's going to be the answer. Let's do another one. Square root of y to the 16. So again, what we need to do is we're going to have to rewrite y to the 16 into y to the certain power to the second power. All right, so what power should we attach to that y? Well, what times 2 is going to give us 16? You can find that by doing 16 divided by 2. That will be what, 8? Okay, so now this it's going to equal to, since remember there was an invisible 2 sitting there, so they're going to cancel each other out, they meaning index and a power, and that's just going to give us y to the 8 in the absolute value. Now we're going to have to analyze this a little bit further. Let's take a look at y to the 8. Okay, so do you see that no matter what the y value is, whether if it's positive or negative, if I raise that number to the 8th eventh power, in this case 8, do you see that no matter what, it's going to be positive? So for example, if I have something like negative 1 to the 8, that's just going to give us a positive 1. 1 to the 8 is just going to be positive 1, and so forth. So here, you already have a positive quantity inside of the absolute value. So in that case, what you need to do is you need to drop that absolute value. And our answer is just going to be y to the 8. Now, I should explain that for the part A as well. Now, part A, do you see why I left that absolute value sign? Because look, let's take out x to the 3rd. Now, depending on whether x is positive or x is negative, our outcome can be negative. Because look, if x is negative 1, we have negative 1 to the 3rd is going to give us negative 1. But we're talking about the square root to begin with. So just to guarantee that our radicand is going to be positive, we're going to have to put an absolute value bar around x to the 3rd. So basically, it's going to go like this. If you're given an eventh root, just apply the property, nth root of a to the n equals the absolute value of a. Now, if that what's inside of the absolute value has a possibility of becoming negative, then you keep that absolute value around it. Now, if you know for sure that what's inside of the absolute value is always going to be positive no matter what, then you drop that absolute value. Don't worry, we're going to do a couple more examples. Let's look at part C, fourth root of y to the 8th. So now what we're going to do is we want to rewrite this guy as y to the what power to the 4th power is going to give us y to the 8th. So what times 4 gives 8? That's 2. Does that make sense? Does y squared to the 4th power, does it give us y to the 8th? I think so. So according to the theorem above, this is going to become absolute value of y squared. All right, now I'm going to ask you this. Can I drop that absolute value or not? Well, I think we can, because look, whoever sits inside of the absolute value, no matter what, it's going to be positive. Do you see that? Because you have a y squared. So no matter if y is positive or negative, you're always guaranteed that our answer is going to be positive. So in that case, we drop that absolute value and our answer just becomes y squared. So let me just write like this, always positive. That implies that drop the absolute value. Okay, now let's look at D, fourth root of y to the 20th power. Well, we're going to do the same thing. We're going to try to rewrite y to the 20 into y to the what power to the 4th power is going to give us y to the 20. Well, I think that number is 5 because 5 times 4 gives us 20. So again, since we're given the eventh root, our answer is going to be absolute value of y to the 5th. Okay, now think about it. Can I drop that parenthesis, not the parentheses, sorry, absolute value or not? Well, I think we need to keep it because this guy can be negative because the exponent on the y is odd. So this can be negative. So in that case, cannot drop that absolute value. Alright, so our answer is just going to be absolute of y to the 5th. Alright, now let's take a look at example 6. Simplify square root of 16x squared. Okay, so in order to do this, well, we're going to start out nice and easy. You can already see that 4 squared gives 16. So here, what I'm going to do is rewrite this as 4 squared times the x squared. Now, how your textbook does it, so this is same thing as 4x whole quantity squared. Okay, now since there is an invisible 2, so the index and the power matches up. So what we're going to get is just the absolute value of 4x. But 4 is always going to be positive no matter what. But x can be negative. So here our answer is going to be 4 times the absolute value of x. Another way to think of it is this. This is same thing as square root of 4 squared times the square root of x squared, isn't it? So what's square root of 4 squared? That's just 4. And square root of x squared just gives us absolute value of x because we're given the eventh root. So we still get the same answer that way. Alright, let's look at B. Cube root of 64 times p to the 6th power. Okay, so this is how your textbook does it. So your textbook says that they already know that 64 p to the 6 is going to give us 4p squared to the 3rd power. You're like, how in the heck did they get that, right? So this is what they're doing. I'm just going to show you how to do this step by step by step. So first, what I'm going to do is I'm going to break down that 64 into a product of primes. So 8 times 8 is 64. 2 times 4, 2 times 4, 2, 2, and then 2, 2. So how many 2's we got? 1, 2, 3, 4, 5, and a 6. So 64 is a 2 to the 6th power. Okay, so I'm just going to work it down here. Okay, so here what we got now is cube root of 2 to the 6 times p to the 6. Okay, so now since you're given the cube root, our job is to try to rewrite this as cube root of 2 to the some power to the third, p to the some power to the third. That's our job. Alright, so what can we insert in there? Well, it looks like 2 times 3 gives us 6. So what's going to happen is, since cube root and power of 3 matches up, what's left of it is just 2 squared times p squared, which is going to give us 4p squared for the answer. So if your textbook just does it without any steps, you can always break it down into product of primes and then go from there. So again, if you just take a look at the textbook way, so from here to here, there you go, boom, here's your one step, and then since the power is going to match up, our answer is just going to be 4p squared as well. Okay, so what I want you to notice is this, because I want to show you how I would do it. So to me, this method is a lot simpler, but you just have to understand why this happens. So notice that, let's take the same problem, part B. Given cube root of 64p to the 6, I broke that down into a product of primes, which turned out to be 2 to the 6 times p to the 6 in the radicand, as a radicand. And that turns into 2 squared times p squared. Okay, so this is the key part right here. From here to here, do you notice what happens here? Do you see any relationship between those numbers? We got a 3 as a cube root, 6 as a power, and the resulting powers are 2 and a 2. So doesn't it look something like this? Well, if I take 2 to the 6 and then divide it by 3 because we're given the cube, and then here we're going to do the same thing, p to the 6 dividing by 3 because that's the number of the root. That's not going to give us p squared 2 times 2 squared. That's exactly what's going to happen. So if that didn't make sense, let's take a look at another example. Let's look at fourth root of 81 x to the 28. Okay, so first what I'm going to do is I'm going to break it down into a product of primes. So I'm going to go 81, 3, is that right? So 81 is 3 to the 4th power because we have 1, 2, 3, 4. Alright, so let me just rewrite it. So this is same thing as the fourth root of 3 to the 4th times x to the 28. Yes, of course you can write x to the 28 in terms of x to the what power to the 4th power. It's going to give us 28. You could totally do that. That's fine. But if you do it my way, right, this is what's going to happen. So this is going to equal to 3 to the 4th dividing by its root, which is 4, multiplying here by x to the 28 dividing by its root, which is 4. So here what we're going to get is 3 times x to the, what is that, 7? So that's your answer. Oh, but the thing is, you're given the fourth root, so we're going to have to be careful there. Sorry about that. X can be any positive or negative number, so I better put an absolute value around x to the 7. So that's going to be the answer. So I'm going to call this method here Dr. Knox way. Alright, but anyways, let's take a look at another one. Let's look at square root of 144 p to the 12th q to the 20th power. So if you recognize that 144 is 12 squared off the bat, that's awesome. Just rewrite that as 12 to the 2nd power. Now, suppose you didn't know. Let me show you how to do it. So here's your 144. It's even, so 2 is going to go in no matter what. So if I divide that by 2, what do we get, 72? Now divide that guy by 2, 36. That's still even. Divide that guy by 2, 18. And then divide that by 2, and then 9, and then here comes 3 and a 3. All right, so let me just write this guy as 2 to the, well, how many 2's? 1, 2, 3, 4. 2 to the 4th times 3 to the 2nd power. All right, so this is same thing as the square root of 2 to the 4th times 3 squared times p to the 12th power and then q to the 20th. All right, now since you're given the square root, there is that little invisible 2 sitting right here. Don't forget that. So if you do it my way, this is same thing as 2 to the 4 over 2, 3 to the 2 over 2, p to the 12 over 2, and then q to the 20 over 2. So which is going to give us 2 squared times 3 times p to the 6, and then q to the 10th. So here you're going to get what? 2 squared is 4, 4 times 3 is 12. So the 12, and then p to the 6, and then q to the 10. Notice that I don't need to put the absolute value around p nor q because they're both raised to the eventh power. So no matter what, our output is going to be positive regardless of p and q are positive or negative. So I'm just going to box that for the answer. How you guys all doing? Don't worry, we're going to do more examples because you know how I roll. Examples after examples after examples. So let's take a look at the next one. Alright, example 6, simplify square root of 225 m squared times n to the 6th power. Alright, so I'm getting tired, so I can't figure it out what square is going to give me 225, so I'm just going to break it down. So I see that 5 is going to go in, so 225 divided by 5 is 45. And then dividing that guy by 5, that's going to be 9, and then here comes your 3 and a 3. So 225 is 5 squared times 3 squared. Alright, so I'm just gonna insert that in. Again, I'm doing this my way. That sounds so arrogant, I'm sorry, but I'm just gonna do this a little shorter way maybe, or less thinking. So this is gonna be the square root of 5 squared times 3 squared, m squared, and then n to the 6th. Alright, since we're given the square root again, remember there's that little invisible 2 sitting there. So this is gonna be 5 to the 2 over 2, 3 to the 2 over 2, m to the 2 over 2, and then n to the 6 over 2. So this is gonna be 5 times 3 times m times n to the 3rd. So it looks like we're gonna have 15 times m times n to the 3rd, but notice that m can be positive or negative, so you're going to have to put an absolute value bar around m no matter what. Similarly for n to the 3rd. N to the 3rd can be negative if n is negative, so you're going to have to put absolute value around the n to the 3rd as well. So combining them together, we're going to have 15 times the absolute m times n to the 3rd. So that's going to be the answer. Let's look at the next one. Square root of 169 x to the 10 y to the 14th. Why don't we just pause the video for a little bit and try this on your own and see what you get. And why am I pausing? I don't know, but okay, so I'm going to pretend that you paused it and you actually try this problem. So let's work it. So let's first look at 169. There's 3 going, 5, no, 7, no, 9, no, 11, no, 13. Is 13 times 13? Yes, yes. So we got 13 times 13. So this is, 169 is 13 squared. All right, rewrite. So this is same thing as 13 squared times x to the 10, y to the 14th. Okay, I'm going to use my trick. So this is same thing as 13 to the 2 over 2, x to the 10 over 2, y to the 14 over 2 because you're given the square root. So this is just going to be 13 times x to the 5th and then y to the 7th. Okay, now let's talk about the absolute value. Do we need it around x? Yes, because when x is negative, a negative number to the 5th power is going to give us a negative. Same thing for y to the 7. If y is negative, it's going to give us negative, but you're given the square root to begin with. So you better put an absolute value bar around it. So this is going to be 13 times, that's the absolute value of x to the 5th, and then y to the 7. And you're done. Don't worry, we're going to do more. Cube root of 64 x to the 15 y to the 66. All right, we're going to do the same thing. So I'm going to break down 64. Is that right? 2 and a 4, 2 and a 4, 2, 2, 2, 2. How many 2's we got? So we got 1, 2, 3, 4, 5, and a 6. So it's 2 to the 6. All right, so rewrite. So this is cube root of 2 to the 6 times x to the 15 times y to the 66. Okay, so this is same thing as 2 to the 6 over 3, x to the 15 over 3, and then y to the 66 over 3. So which gives us 2, what is that, squared times x to the 5th, and then y to the, what is that, 22? Okay, so it looks like we're going to have 4 times x to the 5th, and then y to the 22. Now let's talk about the absolute value. Do we need that around the x? Yes, because if x is negative, negative to the 5th power is going to give us negative, but wait a minute, my bad. You're given the cube root to begin with, so it doesn't matter whether x is positive or negative and y is positive or negative. So guess what? That's going to be the answer. No absolute values needed. So let me erase that. And I'm just going to box that for the answer. Alright, I hope you guys are doing okay. So far so good. Now you're probably asking this. What if the exponent is not divisible by the root? So for instance, which one's easier? So let's look at part B. So suppose I was given square root of 169 and then x to the 9 and then maybe y to the maybe 7 or something like that. Okay, so if I use the same trick, this is going to be 13 squared and then x to the 9, y to the 7th. And so here, if you did it my way, then you're going to have 13 to the 2 over 2, x to the 9 over 2, and then y to the 7 over 2. So do you notice that 9 and 7 are not divisible by 2? So what are we going to do about that is going to be our next section. But let me just show you how to do it since we just learned this. And it might come back to you when we go over the next section. So the trick is that I'm going to keep the square root of 13 squared and then x. Now let's look at the exponent 9. So the trick is this. You want to rewrite x to the 9 in terms of maybe x to the 8 times x to the 1st. Remember, you add the exponents. So if I have x to the 8 times x to the 1st, that's going to give us x to the 9. And we're going to do the same thing for the y. What's the biggest number before 7? That's going to be divisible by 2. Well, that's 6, isn't it? So we're going to break it off at a y to the 6 times y to the 1st. And that's going to give us y to the 7th. So now let me just circle the one that's going to be divisible by 2. So these exponents are going to be divisible by 2. All right, so, but what about the x and a y? Well, this is what's going to happen. That poor x and a y, they're going to be trapped inside of that square root. But everybody else can go outside. Now, how are they going to go outside is this. Let me just bring it over here. Now, if I apply the same trick, 13 squared, square rooted, gives us just 13 to the 2 over 2, which is just 13. And then x to the 8 over 2, it's going to give us x to the, well, I'll just write everything out. 8 over 2, so 2 over 2 here, right? And then y to the 6 over 2. But these poor guys, x and a y, they cannot get outside of the square root. So our answer is going to be 13, and then this is x to the 4th, and then y to the 3rd times the square root of xy. But let me just put the absolute value around y to the third. And don't worry, we're gonna go through this again in the next section. And I'm just gonna stop here. So great job once again. And hang in there. And if you have any questions about this, please let me know. Great job, everyone. And I'll talk to you soon. Bye.